Good day, erudites! Welcome to Next Level Catch-Ups 2.0 for General Chemistry 1. I am Athena Arago, your lecturer for today's video. And in this video, we will be discussing about gas stoichiometry, average kinetic energy, and Clausius-Clapeyron equation. Starting off with gas stoichiometry, this is the calculation of reactants and products in a chemical reaction involving gases using the ideal gas law for non-STP conditions or the molar volume of 22.4 liters per mole at standard temperature and pressure. So gas stoichiometry is just the same as the stoichiometry that we had back in our first midterms, but of course we are dealing with different values of molar masses or molar ratios that depends with each gas given. So for our first example for gas stoichiometry, we have calculate the volume of carbon dioxide at 27 degrees Celsius and 785 torr. That could be obtained by heating 12.8 grams of CaCO3. And the given equation, we have CaCO3 decomposes and produces CaO plus CO2. So the first step is to identify what formula we will be using, and we will be using the ideal gas law, which is PV equals nRT. And since we are dealing with the volume, we are finding for the unknown volume, we can derive the formula into V equals nRT over P. Next, we must get the value of N, or the moles, of CaCO3 since we are given only the mass of the compound, which is 12.8. So we can use N CaCO3 equals mass over molar mass. And the mass is 12.8 grams, while the molar mass of CaCO3 is 100 grams per mole. Then we can input this in our calculator and we will get 0.128 mole. Now that we have all the values that we need in order to get volume, we can input our values into the derived formula from ideal gas law. So we have V equals 0.128 times the R constant, which is 0.0806. Then our temperature, we just have to add 273.15. And we will get 300.15 Kelvin all over 785 torr over 760 torr. So we will get 3.05 liters for this problem. Next, we have number 2. It takes 2 liters of pure oxygen gas at STP to react completely with aluminum. What is the mass of aluminum reacted? And the given equation is 4Al plus 3O2 when combined produces 2Al2O3. Now the first step in getting the mass of aluminum, we need to find the molar ratio of aluminum reacted and pure O2. So our molar ratio we have 4 moles of aluminum is equal to, or is in ratio with 3 moles of O2. So our ratio will be 4/3. Now that we have our molar ratio, we can get the moles, the number of moles of O2. So NO2 is equal to 2 all over 28.4, which gives us 0.08928571429 moles of O2. Then we have to multiply with the molar ratio, which is 4/3. It will give us 0.11904761 moles of aluminum. So now that we have the number of moles of aluminum, we can then multiply it with the mass of aluminum. And the mass of aluminum is 27 grams. So we can multiply 0.119047619 times 27 grams equals 3.214285714. And we have to satisfy the number of sig figs, so we get 3.21 grams. For our last example of gas stoichiometry, what is the mass of NaN3 must be reacted to inflate an airbag to 70 liters at STP. So the given equation is 2 moles of NaN3 decomposes and produces 2Na and 3N2. So our molar mass of NaN3 is 65 grams per mole. We can get the number of moles, which is N equals 70 from 70 liters all over 22.4, since 22.4 is the constant whenever it is at standard temperature and pressure. So we will get 3.125 moles of N2, and our molar ratio for this equation, it is 3 moles of N2 in ratio with 2 moles of NaN3. Now our ratio will be 2/3. Since the unknown is NaN3, we need to put it on top or at the numerator. Now we can multiply the number of moles with our molar ratio fraction. So 3.125 times 2/3, we will get 2.0833. Then we can now multiply with the molar mass of NaN3, which is 65 grams. Then we will get 135.4, but we have to satisfy the number of sig figs, which is only 3, and we will just round down to 135 grams. Next, we have average kinetic energy. This is the average energy of motion of the individual particle within a substance. This is the measure of the particle's random movement and is directly proportional to the substance's temperature. So the hotter the substance, the faster the particles move, which leads to a higher average kinetic energy. So for the formula of average kinetic energy, we have Ke equals 3/2, then times the Boltzmann constant times temperature. So remember that the temperature must always be in Kelvin. Then our Boltzmann constant is 1.38 times 10 to the power of -23 joules per Kelvin, which are directions of forward, backward, sideward, so left and right, as well as upward and downward motions. For average kinetic energy, we can use these formulas. Ke equals 3/2, then the Boltzmann constant times temperature. Then for other cases, when we are asked to get the average kinetic energy per mole, we have to use the R constant. So Ke equals 3 over 2 times R times T, while we are also sometimes going to use the root mean square speed formula in some other cases. So VRMS equals the square root of RT all over M. So for our first problem, we have find the average kinetic energy per molecule at 927 degrees Celsius. So for the temperature, we have to add 927 degrees Celsius plus 273.15 to convert it into Kelvin. So we have 1200.15 Kelvin. Next, we can input our values into the formula, which is 3 halves times 1.38 times 10 to the 23rd negative 23rd times 1200.15. Then we will get 2.48 times 10 to the power of negative 20 joules for the first problem. Next, at what temperature will average kinetic energy be double at 27 degrees Celsius? So we have to find the kinetic energy of a gas at 27 degrees Celsius first. So let's convert 27 degrees into Kelvin. So we will have 300.15 Kelvin. Then to get the average kinetic energy, we have to input our values. So at 27 degrees Celsius, we have 6.21 times 10 to the negative 21 joules. Now, this problem is asking us at what temperature will average kinetic energy, or the value that we got, which is 6.21 times 10 to the negative 21 power, be double. So we have to double this quantity. So we can use or derive the formula. So 2 times 6.21 times 10 to the negative 21 times 3 over 2 times 1.38 times 10 to the negative 23 and temperature. Now, we can derive this formula to get T equals 1.24 times 10 to the negative 20, which is from here. And then our denominator is 3 halves times 1.38 times 10 to the negative 23. And after inputting this into your calculators, we will get 600 Kelvin. And lastly, at a certain temperature, the root mean square of an oxygen molecule is 480 meters per second. Determine the average kinetic energy per molecule and per mole. So our first step is, of course, to get the molar mass of oxygen, or to identify the molar mass, which is 32 grams. And for our VRMS formula, we use kilograms in our mass. So we have to convert it into kilograms. We just have to move it 3 decimal places to the left. So kilograms per mole. Next, VRMS equals 3RT all over M. So our root mean square speed is 480. Then you have to square it or raise it to 2 to remove the square root in the formula. So 3RT all over M. So when we simplify, we will get 23,000 or 230,400 equals 3 times 8.314 times the temperature, which is unknown, all over 0.032. So when we derive this, we will get T equals 230,400 all over 779.4375, which is this all simplified. And we will get 295.7 Kelvin. So this will be the temperature that we will be using to get the average kinetic energy of oxygen. So Ke equals 3 over 2 times 1.38 times 10 to the negative 23 times 295.7. And we will get 6.12 times 10 to the negative 21 joules. This is per molecule. Now we have to divide 6.12 by 2 since we have 2 oxygen molecules. So O2. Now if we divide this, we will get 3.06 times 10 to the negative 21 joules per mole, which is one singular oxygen atom. So here are the final answers for number 3. Lastly, we have Clausius-Clapeyron equation. So the Clausius-Clapeyron equation is the thermodynamic relationship that describes how the vapor pressure of a substance changes with temperature. And this is used to estimate a substance's vapor pressure at a different temperature, calculate the heat of phase transition, and construct vaporization curves. So the molar enthalpy of vaporization, or letter L, capital L, is the energy required to vaporize 1 mole of a substance. This value must be in joules per mole. So this will be the formula for Clausius-Clapeyron equation. So ln of pressure 2 over pressure 1 equals negative molar enthalpy of vaporization, or we can simply write it as L over R, and our constant is 8.314 times 1 over temperature 2 minus 1 over temperature 1. For Clausius-Clapeyron, we will be using the formula ln of P2 or pressure 2 all over pressure 1 equals negative L over R times 1 over T2 minus 1 over T1. So number 1, at 213.1 Kelvin, a substance has vapor pressure of 45.77 mmHg, and at 243.7 Kelvin, it has vapor pressure of 193.1 mmHg. Now, calculate the heat of vaporization in kilojoules per mole. So the first step is to, of course, input the given values into our formula. We have ln over 193.1 over 45.77 equals negative L, which is yung heat of vaporization, and then the R constant times T1, which is 243.7, minus T2, which is 213.1. So if we calculate this, we will get 0.000058928 2674. And this one, if we simplify, we will get 1.439579335. And this will make the process easier. So if we derive L, we can combine these two, or we can divide 1.43 and so on by 0.00058. So the value we will get is 2443.167014 times the R constant, because it is found at the denominator, so you have to multiply in order to cancel out. And we will get 20.31 kilojoules per mole for number 1. Next, a substance has a heat of vaporization of 16.69 kilojoules per mole. So this is our L value. And at 254.3 Kelvin, it has vapor pressure of 92.44 mmHg. Calculate vapor pressure at 275.7 Kelvin. This is the unknown. Our P2 is the unknown. So let's input our values into the formula. So ln times P2 over 92.44 times 16,690 all over 8.314 times temperature 275.7 minus 1 over temperature 1, which is 254.3. So if we process the right-hand side of the equation, we will get 0.612741. And if we process the ln, and if we derive the formula to get P2, we can use P2 equals e raised to 0.612741 times 92.44, 1.845483 from e raised to 0.612. So let's simplify. We will get 170.6 mmHg. And lastly, a substance has vapor pressure of 0.0202 atmosphere at 261.5 Kelvin. If its heat vaporization is 20.54 kilojoules per mole, calculate the vapor pressure at 240.4 Kelvin. So our unknown is the second pressure. So Ln times P2 over 0.2020 equals negative 20,540 over 8.314 times 1 over 240.9 minus 1 over 261.5. So same process. If we simplify the right-hand side, we will get negative 0.8236171558. And then if we derive P2, we just have to raise e to this value that we got, then multiply by 0.2020, which will give us 0.08865 atmospheres. And that's it for today's lecture. Thank you for watching, and we hope you learned something new, and I'll see you again in the next one.